So hello world, welcome to this session on getting started with observability for chaos engineering. So this is Sarna and Ajesh, your host for the session. So without much delay, please welcome our speaker, Shelby Spees, who is developer advocate at Honeycomb, where she helps developers better understand their services in production in order to deliver more business value. So before Honeycomb, our speaker has worked on applications, building pipelines, infrastructures, and other reliability efforts. She is highly passionate about improving access and equity in tech as well as helping people enjoy their work. She is from Los Angeles, where she enjoys doing karaoke with her Pitbull, Nova, etc. So in case you have any questions, please feel free to type in the event chat or the Q&A section, and you can also interact with our speaker so that you can just raise your hands. We can invite you on the stage. And you can also post your queries in the dedicated Slack channels. For those, I'll be sending the link in the event chat in a while. So hope you enjoyed this session. Yeah, so over to you, Shelby.
Thank you so much. I'll go ahead and share. Thank you, Strania. Hi, and welcome to Getting Started with Observability for Chaos Engineering. As was introduced, I'm Shelby Spees. I'm a developer advocate at Honeycomb. And we perform chaos experiments so that we can find the dark corners of our systems during the day when everyone is online and fully caffeinated, right? We don't want to have to discover those dark corners at 3 a.m. when we're getting paged. But not all teams are open to chaos engineering. You might propose the idea and hear from management, oh, no, we already have enough chaos around here. And honestly, not all teams are ready. You might be fighting so many fires that you don't have time to invest in reliability. But even on teams that are all in and performing experiments, you might not be learning everything you could be. We need observability. And what is observability? Well, in software, it's the ability to understand and explain any state a system can get into, no matter how novel or bizarre, without deploying new code. This isn't about going in and changing your log level to debug in production, or going in and adding new timers around blocks of code that you think might be introducing latency. That requires a deploy. Observability is the ability to answer new questions about our systems using the same data we're already capturing. And that's what allows us to learn more from chaos, both the chaos that's inherent in our complex distributed systems, as well as the chaos we're injecting as part of our planned experiments. Observability also helps us decide when and how to experiment so we can better account for business risks. And this makes it easier to get leadership on board with chaos engineering if they've been hesitant about it. There's lots of great observability tooling out there. Honeycomb's not alone, and I've been really excited to see the space grow. But I'm going to be sharing a bit about how Honeycomb works under the hood and about what we do on our engineering team. Honeycomb is a system analytics tool. It's about interacting with data. And it works by ingesting your system's telemetry data, where telemetry is data gathered about the state of your system at runtime. It can come in the form of metrics, logs, traces, structured events. And really the word comes from distance, like telephone, telegraph, and metry, like metrics, measurement, telemetry. And we capture telemetry. For Honeycomb, we were built to support telemetry in the form of structured events. Basically, JSON blobs that capture your runtime context like you have with logs, alongside your benchmarking data like what you have with stat-C timers, but it's all together in a single format, in a single blob. And that structured event format, it also supports trace visualizations, and capturing all this context together allows you to ask novel questions later on, the sort of thing you didn't specifically instrument for at the time you wrote the code. At Honeycomb, our big thing is fast querying. So we built a storage engine from the ground up to support fast querying on arbitrary fields. And that's how, as a user, you don't need to decide in advance what telemetry is going to be important someday. You don't have to say, I want to index on this particular column, because we index on every column. We index on every field. And so how do we know that we're doing a good job? We need to be able to make changes and experiment without negatively impacting customers. And we don't want to take risks when people are already unhappy with their user experience. We want to take extra risks on top of that. We don't want to be rolling the dice and start taking servers offline or injecting latency unless we're confident about the impact on the business, because technical decisions are business decisions. even if they don't feel like it on the surface. At Honeycomb, we measure how well we're doing with service level objectives, or SLOs. And Charity Majors, our CTO, likes to say that SLOs are the API for your engineering team, which means that SLOs are a common language between engineering and business stakeholders. They help us define what success means and help us measure it throughout the lifecycle of a customer. We think about events that are relevant to the business, that homepage loads load quickly, user run queries return results fast, customer data we're trying to ingest gets stored successfully. And each of those types of events has runtime contacts that we collect in our telemetry, from the response code to the user agent to individual query parameters. And then we defined a service level indicator, or SLI, to categorize events into good and bad buckets. We set a threshold, for example, that the homepage should load within 300 milliseconds, and then for each individual homepage load, the SLI determines whether it meets that threshold. Is it good or bad? So that's for individual events. But in order to measure risk, we need to look at the overall context, the overall behavior of our system. We can't just say, oh, well, we had a major outage on Monday, but we've had 100% uptime since Tuesday, so we're safe. Well, it's only Thursday. People still feel that pain from back on Monday. So we calculate what percentage of events were good over the past 30 days and compare that to our SLO target. So, for example, we say 99% of homepage loads in the past 30 days should be fast enough, and we set a threshold for fast enough. So why not aim for 100% or 99.999%? Well, a good SLO keeps your users just happy enough. Each additional 9 in your SLO is an order of magnitude more effort to maintain, and it's often not even worth the effort in situations where people are willing to hit the reload button, or when your system will recover. A little bit of buffering when you're watching a YouTube video, it's not the end of the world. And so your job as a practitioner, as an engineer who's supporting the business, when defining your SLO, is to determine how many reloads, how much buffering is acceptable before users will bail and go to your competitor. And this is where having a good relationship between the engineering stakeholders and the business stakeholders becomes really, really important. So once we have our SLO defined, that allows us to calculate our error budget. How many bad events we're allowed to have in our month-long window, for example. For instance, if I'm serving 1 million total requests per month, and I'm aiming for a 99.9% SLO target on that form of traffic, that means I can have 1,000 events fail over that month. And just like with a financial budget, the error budget gives us wiggle room, which we want in case of an emergency. That error budget is also what tells us when it's okay to take risks. The thing is, your error budget doesn't roll over at the end of the month. It's like trying to save error budget is like trying to keep extra cash under your mattress instead of investing it. You don't want to let that error budget go to waste. And so if you have extra error budget, that's the time to perform some experiments. That's when you want to release the chaos monkeys. Conversely, you shouldn't be performing experiments when your error budget is tight. If you've had a lot of recent customer-facing incidents, or if your engineers are feeling burnt out and spread thin because they're getting paid so often, even if it's not impacting customers, well, that's the time to invest in reliability and learning. You don't need chaos experiments to learn. It's really the other way around. You need to be able to learn in order to justify performing chaos experiments. So here's an example of one of our SLOs at Honeycomb for ingest latency. We're ingesting the data that our customers send us, and we want that data to be available fast so that people can observe their systems in near real time. That's our goal. So over the past month, we've been well above our target for ingest latency. We've been above 99.9%. But the interesting thing here for me is the budget burn down graph on the right side. The steeper the line, the faster we're burning through that error budget. And so seeing how fast we're burning through our error budget allows us to alert proactively. If something is causing us to burn through our budget so fast that we're going to run out in 4 hours, well, that's when we should wake somebody up. Versus if we're burning slowly and we might run out in a couple days, well, then we can open a ticket and discuss as a team the short-term and longer-term solutions to resolve that. So how do we define an SLO like this? Well, we need to measure events that are relevant to our SLO. And higher quality data is what allows us to set goals more effectively. So this is some actual Honeycomb code with custom instrumentation we've added to capture that runtime context. We're adding fields like, yes, it's a batch. We're using HTTP. Here's the data size in bytes and the number of data points. We don't need to calculate the average or the distribution at runtime. We just capture the raw data, and that allows us to do some math later on. We're also capturing some business logic. Like here, we can't ingest this data because the batch is empty. There's some issue with what the user sent us. So we label that in our instrumentation. It allows us to filter at query time. Oh, this isn't an us problem. It was their fault. It was user error. But even filtering on that, it allows us to see, oh, maybe there's some kind of trend here where people using a particular integration are running into trouble. It turns out, for example, people instrumenting Flask apps are significantly more likely to be sending us empty batches. We should investigate that. Maybe there's something wrong with the integration, or maybe there's something in our docs that people are misunderstanding. And so it gives us a lot of that sort of holistic user experience without capturing necessarily business intelligence data. This is our system telemetry. And so we're also capturing error context, stuff like you normally put into your logs. So if we have a higher number of errors, the actual error body is stored right alongside the rest of our telemetry. And this is the thing where when people talk about the 3 pillars, where you're storing your logs separate from your traces, separate from your metrics, it doesn't allow you to introspect that data and zoom in and out on a particular request and then across overall traffic. But for example, if I say, hey, if it's our fault, show me all the traffic that's our fault. Let's filter by, or let's break down, group by the request endpoint. Or, well, I guess these are all the same request, but group by customer ID, or group by user agent, or group by integration, and show me what's new, what are there any trends there? And so that's why it's so important to capture all of that context at runtime into this structured event format, because from the structured event, you can list your logs, you can search your logs, you can generate traces, and you can calculate metrics. So here I've broken down our actual SLI definition. We don't want collect events. We don't want anything from a deprecated endpoint. We don't want anything with a 400 response. And for this LO, we don't want anything that's their fault. We're just worried about stuff that we filtered out their fault. This is stuff that should be an eligible event, an eligible ingest event. So once we've filtered down to the eligible events, we define a threshold for what makes a good event. And so this is a summary of the rest of our SLI definition. We want 200 response codes. And if it's not a 200, it's automatically a bad event. And we want to normalize the duration. We do a little bit of math to normalize the duration across batch sizes to see what's the average duration what's the average duration within this batch. And so that for rounding, we'd rather round up to be safe. We'd rather have events lean slower so that we're more proactive about latency versus rounding down and making our events seem faster than they really are. So this graph, this heat map distribution, shows all of the eligible ingest events. And the bluish green ones are good events, and the yellow ones are the ones that fail our SLI. So there's sort of a distribution of 500 errors, and then there's quite a lot of 200s that are slow. Not a lot in terms of overall traffic, but as a percentage of the bad events. And then the percentage of good events, the green events, is how we get that 99.9% number. And so that's sort of when you're defining your SLO and your SLI using the same data that you're using for debugging, it gives you a much better picture, much more accurate picture of how well your system is doing. Are you meeting your objectives for what that service should provide? So how do you get started with observability? Well, start where you're at. Use the tools at your disposal. You want observability tooling, but you also don't want to just jump on some exciting bandwagon, right? You need to make decisions that are right for your team and for your business. And so I want you to ask yourself, as you assess the tooling you have, am I able to answer novel questions? How well does it support different data types? Can I capture structured events? And can I turn these structured events into can I answer novel questions with them? Can I look at overall traffic and then zoom in on individual traces and zoom back out, grouping by particular fields? That's what makes a difference. And when we're responding to incidents, when we're investigating, or when we're trying to learn from our chaos experiments, can we ask new questions? And many vendors offer a free trial or free tier. So I recommend starting where you're at, trying out, learning the edges of your existing tooling. And if you decide that it's not right for you, there's a lot out there to try out. I also highly recommend using Open Telemetry. It's a vendor-neutral open source instrumentation framework that's supported by a number of vendors in the community, as well as a large open source community. We're approaching general availability. It's been really, really exciting being able to support this project. And there's auto instrumentation for a number of HTTP and gRPC frameworks and integrations. So when you're adding new instrumentation to your system, you don't have to do everything at once. I like to recommend to people, dip a toe in the water, start with auto instrumentation on one app or service, and do it in the critical path. This is something actually I learned from Austin Parker at Lightstep, where you want to choose something that's core to your business, because that's where you'll do the most learning early on, and you'll start to see, like, wow, I didn't even realize it was doing that on every request. These N+1 queries, or these, just really inefficient cache reads that a lot of people discover right away when you start to add instrumentation, especially when you start to add tracing. But you can even send from your development environment. You don't have to instrument all of production at once. It's more about getting comfortable with adding different kinds of instrumentation. And so I would say deploy a canary branch to a subset of production, or if that's not feasible, you can deploy to your staging environment or your test environment and just start learning from there. And once you've gotten comfortable with that, once you have some instrumentation in production, you can iterate, build on that auto instrumentation, start adding custom fields in your code. And a good way to approach this is by adding instrumentation where there's risk. And risk usually means change, right? And so as you build out features or as you fix bugs, add instrumentation for the things that you would probably put a unit test there for. That's the sort of, like, in the moment, for this particular function, what do I care about? For this particular quest, what do I care about? Those are the custom fields that your auto instrumentation frameworks can't possibly anticipate for you. And you as a practitioner have a lot of power and a lot of insight into what's going to be relevant. And then once you feel comfortable with individual services, you can set up distributed tracing, which a lot of vendors are supporting now. And it's really, really exciting to see something like this example trace, where the API service is calling out to the rate limiter service, is calling out to the auth service, is calling out to this ticket backend, and you're wrapping each individual MySQL query. So you can see exactly where you're spending your time for each part of this request. And so an important thing to be thinking about as a practitioner is when you're designing a chaos engineering experiment, you're not just creating a hypothesis for what your service can do, but also for what your telemetry should be able to tell you. I think that's really, really important. Not to just the service break or not break, but how did I know that it was working correctly? Is my telemetry telling me what I expect it to tell me in the moment? Or, do I have to go in and do the user side testing, the black box testing, in order to see the change in behavior? Could I trace through these chaos events to understand that the failover worked correctly? Without the ability to validate that your experiment is successful and your failover is working the way you intended, you don't really have an experiment, right? You're just introducing chaos without having something that you're measuring and controlling for. And so when designing your experiment, you should make your hypothesis about the system and about how you know the system's working. And finally, I want you to celebrate both the successful events as well as the failures. If you had something that succeeded flawlessly and the redundancy mechanisms kicked in, celebrate the great job your team did building those redundancy mechanisms, right? Like, props to you, that's fantastic. On the other hand, if your hypothesis is wrong, well, congratulations. You now have the opportunity to update your mental models. Really, there's no such thing as a failed chaos experiment, right? Every failure is an opportunity to learn and invest in reliability. And I think this is where the chaos engineering community and the resilience engineering community go hand in hand. We're all just trying to learn from the complexity and the chaos that's inherent in our systems, as well as the chaos we're injecting. So I went through that a lot faster than I expected, and I actually have a few more slides, but I'm going to pause here for questions. I would love to. Oh, I see a couple in the Q&A. Yeah.
Okay, I can see.
Yeah.
I can see a couple of questions on the Q&A feed. So, okay, let me read out the question. It's from Karthik. What do you reckon is the important observability data in the chaos injection framework? Or like, what is the important observability data which chaos engine has to generate?
So this is actually where, if you're performing a lot of chaos experiments, you can start to build in sort of instrumentation libraries or just some auto instrumentation so that your chaos tooling adds to the telemetry that you're already generating. You can start adding custom fields that say, hey, this is part of XYZ experiment, so that you can go and then query for those fields and say, show me all the requests that are part of this experiment. And that's something that you can turn on either code side, or you can just have running in the background, and then the chaos, your scripts will activate it as part of the experiment. And so that's a thing that can be really neat. And it's something we do not just for our experimentation, but also for things like feature flagging, where when a feature flag is active, it sends additional telemetry to say, hey, this is behind XYZ feature flag. So that's where the existing structured data format can be really, really flexible to build on top of and build out and add additional context. And then I see the next question from Karthik. Per-event SLI seems a good way to ensure precise operations. How is this woven into chaos experiment that cuts across the stack? That's a fantastic question. We usually define SLOs and SLIs for particular kinds of workloads. So we call them service level objectives, but they do cut across the stack a little bit. The ingest latency is for successful ingest events. Do they cut through? I can even show you. I have a slide here. Like, does it get from the ingest side into the our partition queue, and does it get indexed successfully? And how long does that take? And so that is a way where you can start to see, we're not isolating ingest to just one like narrow scope of the service. You can have sort of cross-service SLOs. So maybe SLOs are almost a misnomer in that way. And that's where you can also start to define the types of events, especially when you have distributed tracing. You can use a top-level request that sort of acts as an umbrella event to define your SLO by. Do you have working topology dependency process visualizations? That's a great question. Do you mean, does Honeycomb have that, or right now I don't think that's something that we particularly try to visualize. But it's something I've done before, even just like locally using dot files, right, to generate a dependency graph. What you do start to see is with your distributed tracing. This is a real request, right? This isn't some like dependency graph I'm generating from my npm package.json. This is a real request that's calling out from this macros endpoint over to, does this work? Okay. Over to checking the rate limits, and it shows you the actual amount of time for each one of these. And what sometimes you'll see when you start out with auto instrumentation and you want to build on that is you'll see like a big chunk of some big long event that doesn't have anything underneath it. And you're like, I don't know what's happening here. Like, and that's when you want to start adding custom instrumentation to wrap around these individual queries or around this additional like check fraud service call to start seeing like these traces connect back together. And that's where the instrumentation frameworks like Open Telemetry can be really, really helpful, because it handles building this trace visualization under the hood. So you sort of just, I know I'm already inside this macros call. So I know that this check fraud is going to roll up into it. And that's a good way to find these hidden dependencies and the hidden corners of our system using tracing. When creating experiments for distributed systems, do you have any advice for observability events that might pass through multiple systems? Exactly the same answer is distributed tracing. What this looks like, I don't have a good example, but what this looks like in aggregate, you don't start with the trace visualization. You start with something a little bit broader, like you would say, hey, show me all of the SLI events. Or show me all of the, or the ingest events, I guess I should say, or show me all of the query events. And you would look at the distribution like this. And if there's some that are particularly slow or some that are particularly, like having a lot of errors, then that's when you zoom in and say, hey, show me the events that have a lot of errors, or show me the events that are slower than X. Great.
Thanks, Shelby.
Mm-hmm.
Is there any more questions from okay. Looks to be.
Yeah. Thank you so much. And if you'd like to learn more about some of our experiments that we've done, we've written about it on our blog. We write about it on Twitter. And you can reach out to me, and I'd love to share that story a little bit more. Basically, the exciting part is because we performed experiments, we were able to start doing rolling restarts across our entire cluster in each of these services. And it gave us the confidence to migrate to ARM64 Graviton 2 instances for a lot of our workload, resulting in a significant cost reduction. I think it was 40% on one of the services. And we started using AWS Spot instances as well. So this has been a really exciting process. Things like finding out that when a Kafka node comes down and there's been an upstream dependency change in our Chef dependencies, it doesn't come online healthy. So we were able to perform a whole lot of reliability work after that, and it gave us the confidence to migrate all of our workloads. So it's been really, really exciting. And thank you so much, everybody.